Next then we come to what wavelength is. So whenever you have a wave, you would always sort of draw it like this. And as we discussed, if you take any little part of the wave, sort of the rate at which a little part of the wave goes up and down, well, that's the frequency. So where's the wavelength? Well, it turns out the wavelength then is always the distance between these crests here of a wave or the valleys. It doesn't matter which one you want to pick, but just the distance between them. And the way I always remember the way lambda works is because these two little legs on the lambda kind of look like a little measure, right? So in other words, I could have a wave that went up and down like that, and the wavelength, that would sort of be the lambda. You see how one leg is pointing to this peak and this leg's pointing to that peak. It sort of measures the distance between the peaks. So that's sort of how I remember what that symbol's for. But in either case, this distance here between the crests or the valleys is called the wavelength, and we'll just label that lambda. That's what it is. So let me go back to the simulation. I'll show you where it comes from. But again, it's actually a distance. Distance between crests or valleys. So back to the simulation here. You can see, so here's the simulation going. As I sort of run it here, I think this is what we saw last time. Sort of goes, and I hope you see where the frequency is, this thing going up and down and making all the little parts of the wave go up and down as well. But when you stop it, you just can't help but notice that that distance between two peaks, here's a distance right here. Look where the mouse cursor is right here. And here's a distance right here between two peaks. So this distance right here would be the wavelength of this wave, or the two valleys down here. Here's a valley and here's a valley. That would be the wavelength also. So we can put a ruler in here actually. So here it is, and so you can see that as this runs, let me stop it right about there. Yeah, there we go. You can see that this peak is at 2 centimeters and this peak is at 4 centimeters. So the wavelength of this wave is 2 centimeters because that's the distance between either one of these two peaks here. And I said you can also measure between two valleys, which you can. Here's 3 centimeters right here. Here's 5 centimeters right here. The distance between those is 2 centimeters too. So see, the distance between any peaks or valleys is 2 centimeters in this case. So what we would write for this wave over here is we would actually write for the sound wave, if this was that wave on, it's not a sound wave, but if this is the wave on that string, we would write that lambda is equal to 2 centimeters. And we also know just by looking at the data here, or the data down here, that the frequency is 3 hertz. So those are the two things that we're able to write about this wave here. Frequency is equal to 3 hertz. So in this particular wave that we're able to generate on this simulator here, when we get it running, if we choose a 3 hertz frequency, it'll have a wavelength of 2 centimeters. Both of these things are necessary to describe what a wave is, frequency and wavelength. And you can see them all, the interplay right here as it goes. Now, are these numbers always fixed? Well, no, of course they're not. We have control over the frequency. Remember, if I slow this down maybe to 1 hertz like that, you can see that the frequency gets much slower. The generator is going much slower. And then if I stop it, let's say right about here maybe, okay, here's where a peak is right here at 0. And you can see now, where's the next peak? Well, it's all the way over here at about 5.5. And so when I lowered the frequency to 1 hertz, the wavelength grew to 5.5 hertz. So that's another bit of data we could draw on here. So there's another way to sort of, maybe we'll keep this one together as one example when we go to the next one. Then the second wave that I drew is much more gradual. It sort of looks more like this. And this one has that frequency of 1 hertz, but the wavelength went up to 5.5 centimeters. So you see the waves can have different frequencies and different wavelengths like that. Oops, can barely get the arrow in there. All right, let's look at the simulator one more time here. So I hope that sort of concept is kind of clear there, that the faster I make the frequency, the smaller the wavelength becomes. So this is a high frequency with a small wavelength. Here is a very low frequency with a very long wavelength. So the wavelength is so long, I can't even fit it in on the ruler right there. It's so long. So there's definitely a relationship in there. And I just wanted to see, so I go up to 3, it doesn't allow me to type in numbers. I was hoping to put a really high number in there, okay? And so back to here, the iPad, to summary for you here. What we also found here is that it is true then that the frequency here is sort of inversely proportional to the wavelength, or likewise, wavelength is inversely proportional to frequency. So what we sort of said is that when you have a very large f, so a very large f gives a small wavelength. And I'm purposely trying to draw the font small. Likewise, you have a very large wavelength gives a small frequency. They're inversely related. We can keep going with these examples like this. So let me see. A very small frequency. Very small frequency gives a large wavelength. And the last one right here, a very small wavelength gives a large frequency, like that, because they're inversely related. This is an important relationship right here. Wavelength is inversely proportional to frequency, or frequency is inversely proportional to wavelength. Okay. And there's one more parameter which doesn't come up very much, won't come up very much in our discussion. There's one more. Hopefully frequency and wavelength are somewhat clear to you now. This last one here is the amplitude, and you can see that over here. One more control. So the question is, what does the amplitude have to do with anything? It is an important property of the waves. And so the word here is amplitude, and you may know what it means by just the name. Amplitude. Let's watch what happens when I change the amplitude of this wave over here. So if I go up and make the amplitude higher, see the wave just gets larger. Let me slow it down just a little bit there. The wave just gets larger, and if I lower the amplitude, see the wave gets smaller. So the amplitude is sort of the size of the wave along that vertical axis over there. Definitely important, and I'll tell you what it's related to as far as light goes here. So this is basically the size of the disturbance. Size of the disturbance. So if I get that disturbance drawn on here again, so here's the wave. We get all three of our parameters labeled on there. Okay. Frequency is hardest to label because it's not really observable unless you actually see the wave going. So you'd have to do sort of the up and the down, and that would be the frequency right here. The wavelength then is the distance between any two peaks or valleys. There's the wavelength right there. And then the amplitude is how high it gets, like right here. That's the amplitude. Getting a little crammed up here in the corner. And what amplitude is going to be for us here, for light anyway, is almost sort of like the power, brightness, or volume, if you want, for sound. So next time you're at a party or something like that and you want the sound louder, say, hey, turn up the amplitude. You know, you could say something like that. Okay.